Hello, in this video we are finishing our discussion of section 7.3 on the shell method. Specifically, we're working through part 4 in example 1, where we have this region that's shaded here, bounded by the curve y equals the square root of x minus 2, line y equals 2, and then restricted to the first quadrant. And in part 4, we are rotating this region about the y-axis. So the first thing to notice here with part 4 is that we have a different orientation than what we had in the previous parts. Specifically, we have a vertical axis of revolution, and this means that we are going to be integrating with respect to x then for the shell method. If we were using the disk washer method, we would use y. But for the shell method, we need to use x. So our equation, y equaling the square root of x minus 2, is already in the correct variable, written in terms of the correct variable. We don't need to rearrange it like we did for the other parts. But we need to figure out what our bounds of integration, our shell height, and our shell radius are going to be. And notice all of those things are going to change because of the fact that we have changed our orientation here. So we're writing in terms of x. So let's first draw a line segment to indicate a shell that we would rotate around our axis. So remember, shell parallel, so we're going to draw a line segment through our region that's parallel to our axis of revolution, so we end up with a vertical line. So then that means that our shell height is this distance, our shell radius is this distance, and we can figure out our bounds of integration in a minute. But something that I want to point out to you, if we draw the shell height here, this little line segment here, it goes between the x-axis and the line y equals 2. If we drew it over here, it would be the same thing. Here it would be the same thing. But notice if we get far enough, then our shell ends up going in between the line y equals 2 and the curve y equals the square root of x minus 2. So right here, when x equals 2, the bottom function for that stops our line segment changes from the x-axis to the curve y equals x minus 2. So what we end up needing to do in this case then is from x equals 2 to the end there, this is a second region. Okay? Because of the fact that the shell height is going to be given by a different function. So we're going to have to set up two integrals for this region. To take this region and rotate it around the y-axis, we're going to need two integrals. So this implies we're going to have two integrals. Oops. Okay, so for our first region, so this is the region that's highlighted in yellow. Let's start with the shell height. This is the distance from y equals 2 to the x-axis, and remember the x-axis corresponds to y equals 0. So this means that we're going to have 2 minus 0 or just 2. So our shell height is just a constant function 2. Our shell radius is the distance from the line segment to our axis of revolution, which is the y-axis. Now, when we rotated around the x-axis before, our shell radius ended up just being y, because we were talking about just a basic vertical distance. Now that we are rotating about the y-axis, we are talking about a basic horizontal distance. So that means that our shell radius is just going to be x in this case. Okay, the distance from the line segment to the y-axis will always just be x. So that's our shell radius, and then our bounds. We need to find the smallest and largest x values, in this case, for the region that's highlighted in yellow. So that region goes from x equals 0 to x equals 2. So that's our bounds of integration there. X equals 0 to x equals 2. So this means the volume for the first region, which I'll denote as v sub 1, is going to be equal to the integral from 0 to 2 of 2 pi. The shell radius is x, and the shell height is 2. And then we'll have dx. Our second region, which I am going to draw over here. So this is the region highlighted in orange. Our shell height. Now, this is the distance from y equals 2 to y equals the square root of x minus 2, because that's where our line segment goes, from y equals 2 to our curve y equals the square root of x minus 2. So then this is going to be 2 minus the square root of x minus 2, because we're talking about a vertical distance, so we need to do top minus bottom. Our shell radius for this one is going to be this distance. Sorry about that. So, the shell radius in words is the distance from the line segment to the axis of revolution. And our axis of revolution is the y-axis. So if we compare this to the shell radius that we had for the first region, notice that the description is exactly the same, the distance from the line segment to the axis of revolution, the y-axis. Well, if the word description is exactly the same, that would be an indication that the symbolic description would also be the same. And again, we are just talking about a horizontal distance from the y-axis to our line segment. So that means that even though we're talking about a different region, our shell radius is still going to be the same. Since the axis of revolution is the same, the shell radius will be the same. Now this might not make sense to you just yet because it's a different region, so how do we have the same shell radius? Well, it's taken into account by the bounds of integration. For our first region, the bounds of integration go from 0 to 2. So if we're talking about x values from 0 to 2, then that would be from here to there. So our shell radius would be all of these distances here. Now, our bounds of integration for the second region, we go from x equals 2 to x equals 6. Because those are the smallest and largest values for the orange shaded region. So if the shell radius is x and x goes from 2 to 6, then that's going to give us from here to there. So even though the shell radius is the same, since we're considering different x values, we end up picking up this other region instead of the first region. Okay, so if we take all of this information then, I'm going to squeeze this in here. Our volume, our second volume integral, is going to be the integral from 2 to 6 of 2 pi. Our shell radius is x, and our shell height is 2 minus the square root of x minus 2 dx. So we have integrals to give the volume for the two separate regions, but we want the whole thing. So that means then that we are going to add together. So for our total volume, V is going to be V1 plus V2. So that's the integral from 0 to 2 of 2 pi x times 2 dx, plus the integral from 2 to 6 of 2 pi x 2 minus the square root of x minus 2 dx. And yes, you could rewrite or simplify these integrals if you'd like, but it is not required for this problem. So this is our final answer using the shell method. Now in the description just above this video in the lecture, it's noted that the disk washer method is much easier to do in this case. So I'm going to work through that quickly just so that you can see a comparison. And I'm going to redraw the region just so that I have something new to write on, since I already have a lot of notation on the previous one. So we are initially talking about this region here, bounded by the line y equals 2, the curve y equals the square root of x minus 2. We've got the y-axis, the x-axis. This is the point 6, 2. This is next value of 2, 1, 1, 2, and so on. Okay, so if we are rotating around the line, or the x-axis, and we are using disk washer, since it's the same general principle, I'm going to combine those two methods here. It just depends on whether we have a gap or not as to whether we use the washer or disk method. Shell method says that we draw a line that's parallel to our axis of revolution, but disk washer is opposite of that. So I'm going to draw a horizontal line, and notice that there is no gap between this line and our axis of revolution, between our shaded region and our axis of revolution. So no gap means we are just going to have disks, so one radius. That radius value is going to be this. Now, the shell method in this case put everything in terms of x, but the disk method for our radius is going to need it to be in terms of y. So we'll rearrange this function to get x equals y squared plus 2. Then our radius function is going to be the distance from the curve x equals y squared plus 2 to the y-axis, which is the same thing as x equaling 0. So now we have a horizontal line. We're going to have right minus left. So this will give us an y squared plus 2 minus 0, or just simply y squared plus 2. Now I know this is considered a radius, but don't confuse it with the radius for the shell method, okay? It is found differently. Remember the wording, okay? So then we are talking about area of circles here. So we're going to need a pi r squared in our integral. We'll have pi big R of y, which is y squared plus 2 squared dy. We haven't found our bounds of integration yet, but we are talking about a region in terms of y. So y ranges from 0 to 2. So then our integral is from 0 to 2 pi of y squared plus 2 squared. And notice this is much, much simpler than what we did for the shell method, okay? So there are times when the shell method is easier. If you tried to apply disk washer method to the 3 previous parts of this example, it would have been much, much harder. But there are definitely times when disk washer is easier. So keep that in mind, okay? If you are given the choice, if the problem just says find the volume of the solid of revolution, then feel free to pick whichever method you think would be easier. You do need to know how to use both methods, because there will be problems that specifically say use the shell method or use the disk washer method. But if you are given an option, then choose whichever one you are more comfortable with, or choose whichever one you think will be easier for a particular problem. Okay? And that wraps up our information for section 7.3.